In this video, we're going to be looking at the second derivative, the notion of concavity and points of inflection. So the first thing I want to do is define for you or explain to you what concavity is. And concavity is basically the way a graph bends. And so if we have a function that looks like this, looks like a cup or a bowl, it's kind of curved upward, we can call that concave up. And let's look at this situation. If we have a concave up situation, let's draw the tangent line to the curve over here. Okay, we have a tangent line to the curve right here, and it has a negative slope, right? So the derivative is negative at that point, and as it rounds this corner, it becomes less negative, and then it becomes 0, and then it becomes positive as it rounds the corner, and then more positive, right? And so if something goes from negative to positive, we can say that it is increasing. If something goes from negative to positive, we can say that it is increasing. So we know that f prime of x, I'm going to write that in purple, f prime of x is going to be increasing. And just as f prime of x tells us something about f of x, f double prime, or the second derivative, will tell us something about the first derivative. So if f prime of x is increasing, f double prime of x must be positive. Remember, when f prime of x was positive, it meant our initial function was increasing. So f double prime of x positive means our first derivative is increasing. All right, you might need to listen to that a couple of times to be able to understand. Let's look at the concave down situation. So we have a graph that's concave down, and a concave down situation basically looks like an upside down bowl. All right, so that's concave down. And let's analyze what's happening with the tangent lines here. So here we start with a positive tangent line, and as we round this corner, it becomes less positive, and then it becomes 0, and then it becomes negative, doesn't it? And then more negative. So if something goes from positive to negative, we can say that it is decreasing, right? So we know that the derivatives are decreasing. F prime of x is decreasing, and that means that f double prime of x must be negative. Okay? So our concavity doesn't have to be that drastic, and so it often isn't. It might be much more subtle. So I'm showing you some scenarios. The top graph right here is an example of a concave up situation. All right. And I also want to show you that concavity is separate from whether or not the function is increasing or decreasing. So here we have a concave up situation on this top left graph. And this graph is also decreasing, right? So if we read it from left to right, we could see that it's going downhill. So here, this first graph is concave up and decreasing. In the second graph, so the graph on the top right, we have concave up still. Notice it's curved upward, concave up. But this graph is increasing, isn't it? So if we read it from left to right, it's going uphill, it's increasing. So here we have a situation where it's concave up and increasing. The third graph, which is on the bottom left, notice that this is curved downward, so that's concave down, and that graph is decreasing, so concave down and decreasing. And the fourth one, which is down in the lower right-hand corner, is concave down and increasing. So again, concavity is the way the graph bends, and it is separate from whether the graph is increasing or decreasing. You can have concave down and increasing. You can have concave down and decreasing. Okay, so now we have a picture of a graph that clearly shows an area where it's concave up and an area where it's concave down. This first region from here, from 0 to A, is going to be concave up, and then from A on, it's going to be concave down. And the place where it changes concavity, right there, it goes from concave up to concave down, has a special name, and that's called an inflection point. And so over the interval from 0 to A, Since it's concave up, we know that f double prime is greater than 0 over that entire interval, isn't it? F double prime is greater than 0, which means that f double prime of x is going to be positive, isn't it? Over that entire interval. And then in the interval from A on, we have concave down, so that means f double prime is going to be less than 0. And another way to say that is f double prime of x is going to be negative, right? For all x values in that interval. All right, so if something goes from positive to negative, what number does it go through? If something goes from positive to negative, or negative to positive for that matter, what number does it go through? It goes through the number 0. So at this point right here, at the point of inflection, we know that f double prime of x is going to be equal to 0. Actually, since we've labeled that point A, we can say f double prime of A is equal to 0. Now this is important, and we will use this information to help us find our inflection points as well as intervals of concavity. A word of warning though, just because the second derivative equals 0 at a certain point, this does not guarantee that we have a point of inflection. Okay, you'll need to test the concavity on both sides of that possible point of inflection, and if the concavity changes from one side to the other, so if it goes from positive to negative or from negative to positive, then you will know it's a point of inflection. So let's look at the example that we looked at in our last video, and that was f of x is equal to negative x cubed plus 3/2 x squared plus 18x. And what I want you to do is find points of inflection and intervals of concavity. So intervals where we have concave up and intervals where we have concave down. And so remember, we said that where the second derivative was equal to 0, those are possible points of inflection. So let's go ahead and find the second derivative. So we have f prime of x is equal to negative 3x squared plus 3/2 times 2x plus 18, and that can be simplified to negative 3x squared plus 3x plus 18. That's our first derivative. And then our second derivative is equal to negative 6x plus 3. And so our possible points of inflection are where the second derivative equals 0. So I'm going to set negative 6x plus 3 equal to 0. And then I'm going to subtract 3 from both sides, and I get negative 6x equals negative 3. And then I'm going to divide both sides by negative 6. And I get x equals positive 1/2, if I simplify that. So positive 1/2 is our only possible point of inflection. Remember, it does not guarantee that it's a point of inflection. We have to test the concavity on either side. So I, again, like to use a number line. I did this with the first derivative test. I'm going to do the same with the second derivative test. And so we pick a number on the left side of 1/2, and you can pick any number you want. It can be really wacky in the negative direction, or it can be something like 0, because 0 is easy to work with. So I'm going to go ahead and pick 0. And remember where we're testing this. We're testing it in the second derivative, because the second derivative tells us about the concavity. So I'm going to find f double prime of 0. Okay? And so that's going to be negative 6 times 0 plus 3, and that gives me positive 3. And so I like to write it like this. Positive, second derivative is positive, so we have concave up. All right? Second derivative positive means concave up. And that nice little smiley face can remind you of that. And then I'm going to take a number on the right side of 1/2, and we can pick any number we want again. And I'm going to use 1 because it's very easy. Again, we test it in the second derivative because that's the one that tells us about concavity. And so we plug 1 in, and we get negative 6 times 1 plus 3, and that gives us negative 3. And so it's negative. The second derivative is negative, so it's concave down. And notice I have that frowning face. So the concavity changed at 1/2, didn't it? So that means x equals 1/2 is a point of inflection. And now we also know our intervals of concavity. So it's going to be concave up over the interval. I'm not going to write from, I'm going to write over. It's going to be over the interval from negative infinity to 1/2. And I'm not going to include 1/2 because at 1/2 it's neither concave up nor concave down. And then it's going to be concave down over the interval from 1/2 to positive infinity, isn't it?